Hello friends, welcome to Physics with Ben. Don't forget to subscribe, like, comment and share this video to those that need it. Also, turn on the notification bell so that anytime I upload a new content, you will be duly notified. This is the last video on Hooke's law experiment. You may love to click in the description box of this particular video that you are watching, and you will see all video links to the theory on Hooke's law, calculations on Hooke's law, the first experiment on Hooke's law where we verified this particular equation. F is equals to KE, increase, increase, decrease, decrease. We also plotted graph on that experiment. So click the notification and the description box below and you get the video link to all those videos and watch all of them. In this particular video, we are not concentrating on force and extension. We are focusing on using the spring to perform simple harmonic motion. If you have watched my videos on the theory and the calculations on Hooke's law, I made mention of something like this, that we are going to make use of a particular equation that m is equals to Lg over 4 pi squared t squared m minus m, where I was explaining that this m, where is it? Sorry, this is m naught. This is m naught. This m naught stands for the mass of the spring. That is the empty mass of the spring. So in this case, if you place this mass on this spring balance, if you place this mass on this spring balance, we got 52 grams. So in this case, m naught, which is this mass of the unloaded spring, is 52 grams, where m would be the slotted masses and L will be the extension produced at different levels, and then G, L, the extension produced at different levels, and G, the acceleration due to gravity acting on the spring and on the weight in the downward direction, while T squared stands for the period of oscillation, the time it takes, the number of time per number of oscillation, the time to take this to go down and to go up. That is that for that. And then we are going to verify this equation, but the equation we are working with is not actually this one, but the WAEC examiner structured it to be this way. Here is the graph of m against t squared, but here is the graph of t squared against m. You see that? So without wasting more time, let's go straight to the business of today. We are making use of WAEC past question. I want to produce all necessary videos on Hooke's law so that in whichever way they come, you will stand a chance to score 20 over 20 in this particular topic. So you may love to screenshot, or let me read. You have been provided with a rotor stand, clamp and bars, a set of masses, a spiral spring, stopwatch, split cork, and other necessary apparatus. Using the diagram above as a guide, carry out the following instructions. Suspend the spiral spring vertically as shown in the diagram. Suspend a mass hanger on the free end of the spiral spring and add a mass M equals to 50 grams to the hanger. Pull the hanger gently downward and release to set it into vertical oscillations. Determine the time T for 20 complete oscillations. Evaluate the period. Sorry, this is the typo. It's supposed to be capital T here. The period capital T. Good. So, correction effected. Evaluate the period capital T of the oscillation. Also, evaluate T squared. Repeat the procedure for 4 other values of M equals to 70, 90, 110, 130 grams. In each case, determine T and evaluate T and T squared. Tabulate your readings. Plot the graph of T squared on the vertical axis against M on the horizontal axis. Determine the slope S of the graph and the intercepts I on the vertical axis. Evaluate K is equal to 4 pi squared all over S. Take pi equals to 2 over 7. State 2 precautions taken to ensure accurate result. Define Young's modulus and force constants. Watch my videos on theory and calculations and you will see all that in it. Say again, a force of magnitude, So we are good to go. Next up, the table of values. I believe by this time, all of us don't have any issues in generating table of values. I have taught all that in all my videos on experiments. So I'm going to fast forward this video and the next thing you see will be the table of values. Why you also screenshot this and let me see how you will do it. Stay tuned and watch till the end. So I'm done with my table of value. Would you love to see it? Good. I took time to circle every detail that we need. All those places I circled are the places you lay emphasis on when generating your table of values. So this is the practical instruction. You may love to screenshot this. Good. So this is how my table of values looks like. I included some details that were not supposed to be here. I did it because I'm teaching. The table of values for this particular experiment is you need the n number of oscillation on top of the table of values correct. You need this. That is on the composite table. You need this. You need this. You need this and this. But I added this and this and this and this to make this experiment a complete one. That is using one stone to kill two birds. Based on this table of values, you can plot this graph or this graph. That is a graph of M on the vertical axis and then T square on the horizontal axis, where the intercept is the unloaded mass of the spring, or a graph of T square against M, where this is the slope and this is the intercept. You get it? Good. So let's go straight to the point. Performing simple harmonic motion using a spiral spring. In the other video, I tried to explain the meaning of this. This is 20 gram, 20 gram, 20 gram, 20 gram. Oh, sorry, this one is 50 grams. 50 grams. And then the whole of this with this is 50 grams. So the first instruction say we should, you can screenshot this portion so that you can follow me. You may love to be doing everything as I'm doing. You need the WAEC standard graph sheet. We'll come to that. We're not yet done with the experiment, so let's keep this aside for now. So this is this mass and this mass, this spring and this spring, they are of the same size and of the same mass. So the mass of the unloaded spring is 52.00 grams. Good. So the first instruction say we should load the spring with 50 grams. This is 50 grams. And extend it. Before we proceed, we want to, the L knot here is the initial position of the spring. In the I used the same setup in the other video. I didn't change anything. So here is our L knot is a 61.00 cm. It is pointing at 61. 61.1 this time. 61.10 cm. So if I place this just as we did in the other video, we are not laying emphasis on the extension here, so I'll be giving us the feedback instead of bringing the camera closer. I don't waste time. So right here, my extension, that is my X, the new position of the pointer, my X. My X is on 63.1.2.3. 63.3 cm. You see that? So the L in this particular set of experiment becomes X minus L naught. And now put the result here. So my X is a 63.3 minus 61.0. So my L here is a 2.30. I told us I'm using one stone to kill so many birds. So if you made something like this is how to go about it. But for this particular experiment here, the original table of values is this, and this. The two of this, and this, they are out of it. Thank you. So right now we are going to displace this for 20 complete oscillations. Are we good to go? Gently, not too high. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I got 6 seconds. Let me do that for the second time. I didn't want to make this table look so dirty. That's why I did not include T1 and T2 and then average small t. But I got 0.6. I got 6 seconds. Let me do it again. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Whoa! You see that? 6 seconds. And so I record on the time here 6.6 6.81 seconds. 6.81 seconds. So this time we loaded 70. So 50 plus 20, that is 70. Good. And so I will collect new information. This time my x is directly on 64. So my x is at 64.00. The new position of my pointer is 64.00. So my L, the extension L is 64 minus, that is 3.00. So I write 3.00. Good. So I will display this guy for 20 complete oscillations to find the time. Are we good to go? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I got 7 seconds. Let's do that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Wow! So my result this time is 7.63 seconds. So I write 7.63 seconds. Good. So I will increase it to 90. This is 70, 80, 90. Addition of this is 90. This time the position for my x is 64.3. 64.3. 64.3. So 64.3 minus 61. So let me correct this. And so this time my pointer is on 64.3, and 64.3 minus 61.1, I got 3.20. Good. So we are going to oscillate this for 20 complete oscillations again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I got 8.31 seconds. Let's do that again. The frequency of oscillation is getting slower. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. This time, I got 8.25 seconds. I'm not taking average T session, I got my first time, so 8.31 seconds. So I got 8.31 seconds. Good. So the next one is 110. This is 90, 100, 110. 90 plus 20. Good. So this time my pointer is on 65.1. 65.1, all right, 65.10. Sorry, this is 0 here. So 65.1 there minus 61.1. So I got the new length is 4.00. I hope you are recording this with your book as you're watching. Good. So the next thing is to oscillate this thing for 20 complete oscillations again. Let's go. You observe that it is getting slower now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Wow! I got 9.09 seconds. Let's do it again. No, that's not too good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That was not too good. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. This time I got 8.97. So if you want to take the average, which is what I'm not doing in this experiment, I still want to go with my first results. That is approximately 9.09. So I go with 9.09 seconds. And then the last one is 130. 110 plus 20 will give us 130. And this time my pointer is on 66.4. 66.4. So I write 66.40. 66.4 minus 61.1. So here we have 5.30. Good. So we oscillate this thing for another 20 complete oscillations. So let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I got 10.25. So I got 10.25. Let's do it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I got 9.69. Only for the third time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I got 9.69. So Let me do for the fourth time again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I don't get it. Let me do it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Oh, 9.78. For the last time, I'm getting 9.20 almost for 3 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Oh, it's okay. We'll go with this. So we got the 9.75. So this is our table of values. So how do we get the period of oscillation? It is this value divided by 20. We'll put the result here. And we're going to record this table to 3 decimal places. So let's do that together. So the first value is 6.31 divided by 20. I got 0.3450. So I record 0.34. So the t square becomes 0.34 square. That becomes 0.1156. So I record 0.116 to 3 dp. 0.116. So I'm done with my table of values. I hope yours also look like mine. So we have 2 options here to plot the graph of m, this on the vertical axis, and t square on the horizontal, this on the horizontal, or the graph of t square on the vertical and then m on the horizontal. Class activity. For the sake of this video, I am plotting the graph of t square against m. But you should help me plot the graph of m against t square. And verify that m naught is 52.00 gram on the graph. That is the mass of the unloaded spring. M naught 52.00 gram. If your work is correct, the intercept of your graph will give you 52.00 gram. That is the graph of m on the vertical axis and t square on the horizontal axis. Next will be our graph. So pick up your WAEC standard graph and let's do it together. The examiners asked us to plot the graph of t square on the vertical axis and m on the horizontal axis. So we are going to choose a scale, this on the vertical and the m on the horizontal. Good. So for the t square on the vertical, the highest value here is 0.24, and then the lowest value here is 0.116. So we are going to choose a scale that says on t square axis, let 2 cm be equals to 0, 4 cm to be equals to let's see what will happen here. Coming. So based on my calculation, we say that on the vertical axis, let 4 cm be equal to 0.05 units. So right at 4 cm, this is 2 cm, this is 4 cm. So 4 cm equals to 0.05 units. That is on the t square axis. And then on the m axis, let us say that is based on these values. Good. So we are free to draw this line. But before we do that, let's look at that on the horizontal axis, which is the m. The highest value is 130, and the lowest is 50. So this is 50.00. So this is and so on the m axis, we say that 2 cm to 20 units. 2 cm equals to 20 units. So this is, we now draw a line, our straight line here right now. And this is supposed to be our t square slash s square. Good. Then right here will be our this is exactly what you should do. And then here is our 0, 0. 0, so here this is a 20, 40, good. And here we said 4 cm, this is 2 cm to 20, that's the meaning. So this is from here, it is 4 cm, 2 to 4 cm, 4 cm to 0.05. So this is 0.05. Then another 4 cm, this is 0.1. Good. So we are done setting our graph. The lowest and the highest value on the vertical axis are all represented. The highest value here is 0.04, lowest value is 0.01. So the next thing to do is to plot our graph. But before we do that, we're going to find the value for each small box, as we have been doing in all our experiments. Very, very important. So here, this is you have 20 small boxes here. Good. So 0.05 divided by 20, 0.05 divided by 20. So here you have 0.05 divided by 20. The value for each small box is 0.0025. 0.0025 is the value for each small box here. Here we have 20 by 10, that will give us 2. So here is 20 by 10, that will give us 2. The value for each small box here is 2. So at this point, we plot our graph. I'm going to plot the first one, and then we are going to fast forward this video. So for this as decimal value, so we divide everything here as I've been doing by 0 0.0025 to get the value for each small box. Good. So let's plot the first value together, then I'll fast forward this video. We have when the period t squared was 0.116, how do we get that precise value on the graph here? Divide 0.116 by 0.0025. So say 0.116 divided by 0.0025. We got 46. We round it down, 46.4. That is 46 small boxes we take to that point. So this is 10, 20, 30, 40. This is 1, 2, 3, 4, 5, and 6. So at that point, that is where we have our 0.116 against 50. 50 gram. Sorry, I forgot something here. This is mass. Mass in gram. Very, very important. Mass in gram. So 50 is halfway 60 here. So this is 1, 2, 3, 4, 5. This is 50. So where 50 and this point intersects, that is the first point. So you trace this point like this. This is where they intersect at this point here. So we are done plotting the first point. Let's plot the second point. When t squared was 0.144, it was 70. So we say that 0.144 divided by 0.0025. We got 57.6. We round it up, 58. So this is 10, 20, 30, 40, 50. 1, 2, 3, 4, 5, 6, 7, and 8. So this is where we find 0.144. That's this point against 70 gram. 70 gram is between 60 and 80. So this is 1, 2, 3, 4, 5. This is 70 gram. So you trace this point. Then this is where they meet. Then we are done with that point. You always place this ruler so that you don't miss the lines. So we are done plotting the points. What a perfect graph. This is 1, 2, 3, 4, 5. And then we have 1, 2, 3, 4, 5. Good. So the next thing is to draw the line of best fit. This is good. Our line of best fit. Now, I did not observe the trend today. Look at this. You have mass and period. It is increasing down, increasing down. So all increase, or decrease graphs will always give you a graph that looks like this. Always remember this. This graph, or this graph, or this graph. This is y is equals to mx, and this is y is equals to, so mx plus c, y equals to mx. Just y is equals to mx, sorry, y equals to mx here. Here y is equals to mx plus negative c. So obviously this is the graph that we have plotted. You can look at that there. So we draw a line of best fit. This is bad. You can't go with this. You can't go with this. You can't go with this. So let's look at this. Can we catch these 3 points? One here, one in the middle, one here. One this side, one this. This is perfect. So let's go with this. You can't go with these 3 and leave these 2 on this side. So go with the first point, this point, and then this point. This point is this way, is below the line, and this point is above the line. So this is a perfect line of best fit. So we draw it straight down. Always use 30 cm transparent ruler. So we are done with our line of best fit. Good. The next thing is to select our big triangle for the slope. So I will choose this point. And I'll come down here. Down here. Down here. Good. So this will be my triangle for the slope. Always draw a big triangle to avoid having error in your experiment. And then down here you put dot, broken lines, dot, 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 dot. And then here thick continuous line, and then broken lines this side. Up here you put broken lines. Then down here you also put broken lines. So here becomes your change in t square, and here becomes your change in m. Here is your m2, and here is your m1. Here becomes your t square 2. Here becomes your t square 1. Good. So our slope or gradient for the graph becomes change in t square divided by change in n, as we've been doing before. So this is the same thing as t square 2 minus t square 1 divided by m2 minus m1. I believe we don't have issues reading m2 and m1. We said each line here, each box here stands for 2. So our m2 is directly on 120. And then our t squared, let's calculate for our t squared 2 first. Our t squared 2, say to get our t squared 2, say 0.0025 times. This is 10, 20, 30, 40, 50, 60, 70, 80, 90. Yes, 90 times 90. That will give us our t squared 2 in this case becomes 0.225 minus our t squared 1 is directly on 0.05. Directly on 0.05. So write minus 0.05 divided by our m2 is on 120. So we say this is 120 minus this is 2, 4, 6, 8, 10, 12. Our m1 is on 12 minus 12. If we do that correctly, we have 0.225. And so the slope is 0.00162 seconds square per gram. What a beautiful graph this is. What a beautiful graph this is. Wow. So we proceed. You may love to screenshot this graph. I love this graph. So the next line of action, we are done with the graph, and that's the slope or the gradient. The next line of action is the examiners ask us to determine the gradient, the graph, and the intercept I on the vertical axis. The graph cut across this particular point here, and change in intercept I, that is it. So we write that from the graph, our intercept, change in that I, is given to be what? The value for each small box here was 0.0025. So say that 0.0025 times, let's count, this is 10, 1, 2, 3, times 13, times 13. So intercept is 0.0325 seconds square. That is the intercept for the graph. This is the point here. So the next thing the examiners ask us to do is they ask us to evaluate. Take note, the intercept was said to be found on the vertical axis, and that was correctly done. the examiners ask us to evaluate K is equal to 4 pi square all over S. So K is equal to 4 pi square all over S, meaning all over this slope is the same thing as the S. And they ask us to take the value for pi to be 22 all over 7. 22 all over 7. So we write that this implies that our K is equal to 4 times 22 all over 7 all square divided by the value for the slope divided by 0.00162. 62 what? 0.00162. Yes, 62s square that. So if you evaluate that correctly, we have that bracket 22 divided by 7 bracket close square will give us this is the same as 4 times 9.87776 divided by 0.00162 s square that. So 4 times that we have 39.5104 divided by 0.00162 s square that. So we have 39.5104 divided by 39.5104 divided by 0.00162. We have 389.14 gram per second square. Therefore, K is equals to 24,389.14 gram. That is the value for the K the examiners ask us to evaluate. The examiners ask us to state 2 precautions taken to ensure accurate results. State 2 precautions. So precaution number 1, I avoided error due to parallax when taking reading on the meter. I avoided error due to parallax when taking reading on the stopwatch. I displaced the slotted mass gently to avoid random oscillation. You may love to Google and find more of the precautions on this. So those are the 2 main precautions. The last thing we are supposed to do here is they ask us to define the Young's modulus and force constants. I will hesitate to define the Young's modulus here and the force constant. Watch the video I have produced on theory and the calculations on Hooke's law, and you see all that there. And then the other part is a force of magnitude 5 Newton is applied to the free end of a spiral spring of force constant that calculate the energy stored in the stretch spring. I have done all videos on this, so I feel so reluctant answering question BI and BII. Click in the description box below and solve this question and drop the answer in the comment box. To this, we have come to the end of all the video series I promised on Hooke's law. Do me well to watch all these videos, the theory, the calculations, and lastly on these two experiments. Thank you for watching. Thank you. God bless you. Don't forget to subscribe to Physics with Ben. Like, comment, and share. Bye-bye.